scientists' concern about the polyvinyl chloride, or PVC, conduit is valid to some extent. Lightning strikes can induce high-frequency electromagnetic fields, or EMFs, that can penetrate non-conductive materials like PVC. These EMF can induce currents in nearby conductors, including the electrical wiring. If the induced currents in the wiring are high enough, they can damage the insulation or even cause the wiring to melt. However, the presence of a grounding conductor inside the conduit helps to mitigate this risk by providing a low impedance path for the induced currents to flow to ground. Based on the available information, the following mitigation measures are recommended. Firstly, ensure proper grounding. Verify that the grounding conductor inside the conduit is adequately sized and connected to a robust grounding system. Secondly, consider metal conduit. If possible, consider replacing the PVC conduit with ferrous metal conduit. Metal conduit provides a better shield against EMF and reduces the risk of induced currents in the wiring. Thirdly, install surge protection devices at the panel boards to protect the equipment connected to the circuits. Surge protectors divert excess voltage to ground, reducing the risk of damage to sensitive electronics. Fourthly, supplement the existing grounding system with additional ground rods to improve the overall grounding performance. Other considerations include the proximity of the steel structure to the wiring should be considered. The EMF induced by a lightning strike can be amplified by the presence of nearby metal structures. The frequency and severity of lightning strikes in the area should also be taken into account. If the observatory is located in a region with a high incidence of lightning, additional mitigation measures may be necessary. While PVC conduit provides some level of protection against lightning strikes, it is not as effective as ferrous metal conduit in mitigating the risks associated with induced EMF. By implementing the recommended mitigation measures, including the use of metal conduit, surge protection, and improved grounding, you can significantly reduce the risk of lightning-related damage to the equipment in the observatory dome. Let's delve deeper into each of these recommendations, starting with grounding. Grounding is a critical safety measure in any electrical system, but it's especially important in areas prone to lightning strikes. The purpose of grounding is to provide a low-resistance path for fault currents, including those induced by lightning, to flow back to the source. This helps to prevent voltage buildup and reduce the risk of electrical shock or equipment damage. The grounding conductor inside the conduit plays a vital role in this process. It should be sized according to the National Electrical Code, or NEC, to handle the anticipated fault current. Table 250.122 in the NEC provides guidance on the minimum size of grounding conductors based on the rating of the overcurrent protection device protecting the circuit. The grounding conductor should be securely connected to a grounding electrode system, which typically consists of ground rods, ground plates, or a combination of both. The NEC section 250.52 outlines the requirements for grounding electrodes. In addition to the grounding conductor inside the conduit, supplemental grounding electrodes, such as additional ground rods, can further improve the grounding performance. These ground rods should be installed in accordance with NEC section 250.53, which specifies the spacing and depth requirements. Now, let's discuss the benefits of using metal conduit. Metal conduit, such as galvanized steel or aluminum, provides a Faraday cage effect, which helps to shield the wiring inside from electromagnetic interference, or EMI, including the EMF generated by lightning strikes. The Faraday cage works by distributing the electrical charge around the outside of the conductive material, preventing it from penetrating the interior. This significantly reduces the induced currents in the wiring. When selecting metal conduit, it's important to ensure that it is properly grounded. The conduit should be connected to the grounding electrode system at multiple points to maintain a low impedance path to ground. Fittings and connectors used with metal conduit should also be listed for grounding purposes. In situations where replacing the existing PVC conduit with metal conduit is not feasible, alternative shielding methods can be considered. For example, wrapping the PVC conduit with a layer of conductive shielding tape can provide some level of EMI protection. The shielding tape should be properly grounded to be effective. Next, let's examine surge protection devices, or SPDs. SPD are designed to protect electrical equipment from voltage surges, including those caused by lightning strikes. They work by diverting excess voltage to ground, preventing it from reaching sensitive electronic components. SPD are typically installed at the panel boards to protect all of the circuits fed from that panel. They can also be installed at individual equipment locations for more localized protection. There are different types of SPD available, each with its own voltage protection rating and surge current capacity. The selection of an SPD should be based on the anticipated surge voltage and current levels in the area. The NEC Article 280 provides requirements for surge protection devices. When installing SPD, it's important to follow the manufacturer's instructions and ensure that they are properly grounded. The grounding conductor for the SPD should be as short and straight as possible to minimize impedance. Let's also consider the proximity of the steel structure to the wiring. Metal structures, such as steel beams and columns, can act as antennas, amplifying the EMF induced by lightning strikes. This can increase the risk of induced currents in the wiring. To mitigate this risk, the wiring should be kept as far away from metal structures as possible. If the wiring must be run near metal structures, it should be shielded with metal conduit or other shielding methods. Bonding the metal structures to the grounding electrode system can also help to reduce the voltage potential between the structures and the wiring. Finally, let's discuss the frequency and severity of lightning strikes in the area. If the observatory is located in a region with a high incidence of lightning, additional mitigation measures may be necessary. This may include the installation of a lightning protection system, which consists of air terminals, DAN conductors, and a grounding electrode system. The lightning protection system is designed to intercept lightning strikes and safely conduct the current to ground, protecting the structure and its contents from damage. The design and installation of a lightning protection system should be performed by a qualified professional in accordance with the National Fire Protection Association, or NFPA, 780 standard. In conclusion, protecting electrical wiring in an observatory dome from lightning strikes requires a comprehensive approach that includes proper grounding, metal conduit, surge protection, and consideration of the surrounding environment. By implementing these mitigation measures, you can significantly reduce the risk of lightning-related damage to the equipment and ensure the safety of personnel. Remember that electrical work can be dangerous, so it's important to consult with a qualified electrician or electrical engineer before making any changes to your electrical system. They can assess your specific needs and recommend the most appropriate solutions. Now let's get into some more specific details about grounding systems. A well-designed grounding system is paramount for mitigating lightning-induced surges. The goal is to provide a low-impedance path to Earth, allowing surge currents to dissipate safely without causing damage. Several factors influence the effectiveness of a grounding system, including the number and placement of ground rods, the soil resistivity, and the bonding of metallic components. Increasing the number of ground rods reduces the overall resistance to Earth. Multiple ground rods should be spaced at least their length apart to avoid overlapping spheres of influence. Soil resistivity is a measure of how well the soil conducts electricity. Lower soil resistivity results in better grounding performance. Soil resistivity can be improved by adding conductive materials such as bentonite clay or ground-enhancing compounds. Bonding refers to the electrical connection of metallic components to create a common ground potential. This prevents voltage differences between components, which can lead to arcing and equipment damage during a lightning strike. All metallic components, including conduit, enclosures, and structural steel, should be bonded to the grounding system. Let's also consider different types of surge protection devices. There are three main types of surge protection devices: Type 1, Type 2, and Type 3. Type 1 SPD are installed at the service entrance, providing the first line of defense against lightning surges. They are designed to handle high surge currents. Type 2 SPD are installed at panel boards, providing protection for branch circuits. They are typically used in conjunction with Type 1 SPD. Type 3 SPD are installed at the point of use, providing protection for individual equipment. They are often used for sensitive electronic devices. The selection of an SVD should be based on the specific application and the anticipated surge levels. SVD are rated by their surge current capacity, which is the maximum surge current that they can handle without failure. They are also rated by their voltage protection rating, which is the maximum voltage that they will allow to pass through to the protected equipment. Choosing the right SVD is essential for effective surge protection. Now let's move on to conduit selection. While metal conduit offers superior shielding against EMF, it is not always practical or feasible to replace existing PVC conduit. In such cases, alternative measures can be taken to improve the shielding performance of the PVC conduit. One option is to wrap the PVC conduit with a layer of conductive shielding tape. The shielding tape should be made of a conductive material such as copper or aluminum and should be applied tightly to the conduit. The shielding tape should be properly grounded to be effective. Another option is to install a wire mesh around the PVC conduit. The wire mesh should be made of a conductive material and should be grounded at multiple points. The wire mesh provides a Faraday cage effect similar to metal conduit. In addition to shielding the conduit, it is also important to shield the wiring inside the conduit. This can be achieved by using shielded cables or by wrapping the wires with a layer of conductive tape. Shielded cables have a metallic shield that surrounds the conductors, providing protection against EMI. The shield should be grounded at both ends to be effective. When working with electrical systems, safety should always be the top priority. Always disconnect power before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow all applicable electrical codes and standards. If you are not qualified to perform electrical work, hire a licensed electrician. Remember that lightning protection is a complex topic, and there is no one-size-fits-all solution. The best approach is to consult with a qualified professional to assess your specific needs and design a system that meets your requirements. Here are some additional points to consider regarding grounding and bonding in the context of an observatory dome. Firstly, grounding electrode system. The grounding electrode system should be designed to provide a low impedance path to Earth. This may involve the use of multiple ground rods, ground plates, or a combination of both. The grounding electrode system should be installed in accordance with NEC section 250.52. Secondly, bonding of metallic components. All metallic components within the observatory dome, including the steel structure, conduit, enclosures, and equipment, should be bonded together to create common ground potential. This prevents voltage differences between components, which can lead to arcing and equipment damage during a lightning strike. Thirdly, surge protection devices. Surge protection devices, or SPDs, should be installed at the service entrance, panel boards, and equipment locations to protect against voltage surges caused by lightning strikes. The SPD should be selected based on the anticipated surge levels and the sensitivity of the equipment being protected. Fourthly, the lightning protection system. A lightning protection system may be necessary if the observatory dome is located in an area with a high incidence of lightning strikes. The lightning protection system should be designed to intercept lightning strikes and safely conduct the current to ground. The design and installation of a lightning protection system should be performed by a qualified professional in accordance with NFPA 780. Fifthly, regular inspections and maintenance. The grounding system, bonding connections, SPDs, and lightning protection systems should be regularly inspected and maintained to ensure that they are functioning properly. Any damaged or deteriorated components should be replaced promptly. It is also crucial to understand the role of impedance in grounding systems. Impedance, which includes both resistance and reactance, is the opposition to the flow of alternating current. In grounding systems, low impedance is critical for effectively diverting surge currents caused by lightning strikes. High impedance can impede the flow of surge currents, leading to voltage buildup and potential equipment damage. Several factors can contribute to high impedance in grounding systems, including long conductor lengths, sharp bends in conductors, and poor connections. To minimize impedance, grounding conductors should be as short and straight as possible, with minimal bends. Connections should be tight and corrosion-free to ensure good electrical contact. The use of wide, flat conductors, such as copper straps, can also help to reduce impedance. In addition to minimizing impedance, it is also important to ensure that the grounding system is properly sized to handle the anticipated surge currents. The size of the grounding conductors and electrodes should be based on the recommendations in the NEC and other applicable standards. Insufficiently sized grounding components can overheat and fail under high surge currents, rendering the grounding system ineffective. Furthermore, the concept of single-point grounding is essential for minimizing ground loops and noise in sensitive electronic equipment. Single-point grounding involves connecting all grounding conductors to a single grounding point typically located at the service entrance. This prevents circulating currents from flowing through the grounding system, which can cause noise and interference in electronic equipment. Single-point grounding is particularly important in observatories, where sensitive scientific instruments are used. Let's discuss the importance of equipotential bonding. Equipotential bonding is the practice of connecting all metallic components within a structure to create a common electrical potential. This helps to prevent voltage differences between components, which can lead to arcing and equipment damage during a lightning strike or other electrical fault. Equipotential bonding is achieved by bonding together all metallic components, including conduit, enclosures, structural steel, and equipment housings, using bonding jumpers or conductors. The bonding jumpers should be sized according to the recommendations in the NEC. Equipotential bonding is particularly important in areas where there is a high risk of lightning strikes or other electrical disturbances. It helps to create a safe and reliable electrical environment for both personnel and equipment.